Make sure before you do this you've read this FYI and answered the questions. If you haven't done that yet, here's a link. We're going to continue on and try to figure out what can be learned by analyzing the light from astronomical objects. It's called spectrum analysis. Spectrum analysis is probably the second most useful tool that astronomers have, other than telescopes. We finally get to talk about this. We finally get to learn what it is, how it works, and what we can learn from it. Today's question of the day is, what can we learn by observing the spectrum of an object? Go ahead and write that down. Normally we would do this lesson after doing a spectrum analysis lab. However, because we're not in school this year, we're just going to go right into this explanation. First thing that you need to know, there are three types of spectrums. All right, there are a continuous spectrum, an absorption spectrum, and an emission spectrum. They look different, they're caused by different things, but they are all related to each other. I want you guys in your science journal to make this little chart. Once you have this chart made, I want you to do your best to draw a continuous spectrum, an emission spectrum, and an absorption spectrum. Continuous spectrums have all of the colors of the rainbow. Emission spectrums have bright lines, and absorption spectrums have all the colors, but those lines are taken out of the full rainbow. Once you have those etched, let's try to figure out what the difference is between these. A continuous spectrum is released by everything in the universe because it's released by anything that radiates out heat. The light that is being radiated out is spread out in a continuous spectrum where at least some of every single wavelength is being emitted. And because some of every wavelength is being emitted, at least in the visible part of the spectrum, it looks like a rainbow. That doesn't mean that it's the same in every part of the spectrum. Obviously, there's going to be more light released at certain parts of the spectrum, which is why stars can look different colors, but at least some amount of light is released at every single wavelength. An emission spectrum is when hot gases, the atoms in hot gases, are going to release extra light at certain wavelengths, and you're actually going to get bright lines showing up in those spectrums. And every single element in the universe is going to release its own set of bright lines. And if we see a certain set of bright lines, we can identify which element is causing that to happen. So we can look at things that are very far away, and based on the spectrum of light, these bright lines that we see coming from that object, we can determine what's in that object, what elements make that object up. This is what you guys would have seen in the lab, and you would have seen that, for instance, hydrogen has a certain set of bright lines. Helium has another set of bright lines. Lithium has another set. Each and every element has its own particular fingerprint, if you will, of bright lines. This is also why different elements burn in different colors. Why fireworks can be blue or green or yellow, because they put different elements in the gunpowder when it explodes. Because each element has a different number of electrons and protons and electron orbital levels, and they are shaped differently, you're going to get different colors that come out of them. I want you to notice that absorption and emission spectrums are exact inverses of each other. The absorption spectrum for lithium looks like this. The emission spectrum of lithium is just underneath it. Whatever is missing from the absorption spectrum, that's where those bright lines are going to show up for the emission spectrum. So what exactly is the absorption spectrum? The absorption spectrum is when light goes through a colder gas. Some of that light is absorbed and doesn't make it all the way to our detectors. The absorption spectrum then are those dark lines, and those dark lines are going to show up in the same places and can actually tell us which elements are in a distant object. And the reason that this works is because this light source would be giving off a continuous spectrum. This continuous spectrum coming from this object is going to go through a colder cloud of some element. That gas cloud is going to absorb, based on which element it is, very specific wavelengths of light. So the light that then passes through does not have those particular wavelengths of light in it. When it gets to our detectors here, we don't see the light that was absorbed by that particular gas cloud of whatever element it might be. One of the ways that we can tell what giant gas clouds out in space are made out of is because we look at the spectrum from objects behind them, and that light is going to be missing very specific wavelengths of light based on whatever that gas cloud is made out of. It's not just elements either, molecules can do this. One of the ways that we know that there is water throughout the entire universe, it's all over, it might not be liquid, but there are water molecules everywhere, is because we see the absorption spectrum that water would give off. If you look very closely at the sun's spectrum, you will actually notice that it is not a continuous spectrum as you might imagine. It's actually an absorption spectrum. And the reason is that at the photosphere, the surface of the sun, it does give off a continuous spectrum, a little bit of light at every single wavelength. The light then has to go through the chromosphere and the corona. Some of that light is absorbed by the sun's atmosphere. And so by the time it gets to Earth, that light is actually missing quite a few little wavelengths of light. And the sun's spectrum actually looks like this. And each of these little dark lines is because that light, that wavelength of light, was absorbed by some atom up in the atmosphere of the sun. What does this let us do? We can actually figure out which elements are in the sun based on these dark lines. This is the spectrum of a star that's about 13 light years away from planet Earth. Without going to that star, without sending a probe to that star, we can actually determine the exact elements that are in this star because of the little tiny patches of light that are missing. Because it is an absorption spectrum, we know wherever these little dark lines are, that was caused by elements that are in the atmosphere of that very distant star. We know what's inside of that star. But why does this happen? Why do those lines appear? What is causing that to happen? Let's figure that out. We have to start with looking at light a little bit more closely.
We see particle-like behavior every day. Drop a ball on the ground and it follows a single trajectory. Leave your giraffe parked on the street and when you come back, it's still there, just one giraffe. And we see wave behavior too. Toot your horn and waves spread out through the air, carrying sound to the ears of anyone around. Or drive a boat through water and waves travel outwards along the surface. But when it comes to the physics of the very small, what we see is a wave-particle duality. Sometimes very small things, we're talking electrons and protons here, behave like particles, and sometimes they behave like waves, flip-floppers. For example, if you release an electron, it'll travel outward as a wave through the room, but when it hits the wall, it'll only hit in one place. You started with one electron, after all. So what if sound had a wave-particle duality? When you shouted, the sound waves would spread outwards in all directions, but only one person could hear what you said. Or when you drove your boat through the water, the waves would travel like normal, but only hit the shore in one place. Now that would make for some pretty boring surfing. Really small things act sometimes like waves and sometimes like particles.
Turns out that light travels as a wave, but light is also a particle, and that is the important part. Light travels as a wave and it has different wavelengths, but light also can be thought of as a photon, as a very discrete, singular piece of light. It's what's known as the duality of light, and it is something that doesn't make sense to most people's brains. Light is a wave. Light is also a little particle called a photon. Each photon that is released has a very specific amount of energy. Specific amount of energy. Specific amount of energy. The photon next to it might have a different amount of energy, so we could have a photon of red light and a photon of blue light. Two photons, two pieces of light, both with different energy. And atoms can actually absorb those photons or release those photons. If an atom absorbs a photon, it stops that light from traveling through, and if it releases a photon, it's going to cause that bright line to show up. The key to why those lines are in very specific places, though, has to do with the fact that the photons have a very specific amount of energy. And if I have an atom, we have an electron in the first energy level. This electron can absorb energy and bounce out to the second energy level. It can't, however, bounce in between. It can only go to the first to the second. Maybe it'll go from the first to the third or the first to the fourth. It can't go in between. To go from the first to the second is a very specific amount of energy. And only a photon with that exact amount of energy can get this little electron to bounce up to this second energy level. So as soon as a photon with that exact energy hits this electron, as soon as a photon with that exact amount of energy hits this electron, it will bounce up. Electrons always want to be in the lowest energy state though. So at some point, this little electron, after bouncing up, is going to release that energy, and the amount of energy that it releases is a photon of that exact wavelength, that exact amount of energy. So it would be the exact same color that was absorbed when it originally took in the energy. If we have an electron at the ground state, we can get a photon with a very specific amount of energy to bump it up to an excited state at a higher energy level. But only a photon with that exact amount of energy can do that. After a certain amount of time, this electron is going to fall back down to the ground state and release a photon with that exact amount of energy. It can't release a photon of any other energy, only this exact amount, which is going to correspond to an exact wavelength or an exact color. It's actually what's going on over my head that you guys may have been wondering about. We have a star and it releases light in all directions. This light is going to hit this atom, and this little electron will absorb the orange wavelength of light. It will then get bounced up to the second energy level. Eventually, it will fall back down, releasing that amount of energy as an orange photon going in another direction. So if you look closely, you will notice that this electron absorbs an orange wavelength of light, gets bounced up to the second energy level. A little bit later, it will fall back down, releasing an orange photon. Why do we get more than one little line show up? Well, most atoms can have an electron bounce between 1 and 2, 1 and 3, 1 and 4, 1 and 5, maybe between 2 and 3, 2 and 4, 2 and 5, between 3 and 5, between 3 and 6. There are different jumps that electrons can make. And each one of those jumps is going to correspond to a different line that shows up on the spectrum. So when an atom absorbs energy, it's going to absorb that wavelength of light, and the rest of the light will travel on to our detectors, missing that wavelength, and we're going to see a dark line. If that atom then falls back down to its ground state, it will emit that energy, and when that gets to our detector, it's going to show up as a bright line. So as the atom absorbs energy, we get an absorption spectrum, and as the atom emits energy, we get what's called an emission spectrum. The key to this whole thing is to realize that the photon that is emitted or absorbed has to have the exact energy that corresponds exactly to bounce an electron either up to a higher energy level or when it's falling down to a lower energy level. You can't have an electron go halfway in between energy levels. These are very specific amounts of energy to get an electron to move between them, and only photons with very specific wavelengths have the correct amount of energy, which is why we get those very specific lines. And this is what's causing those fingerprints. Because every element and molecule in the universe is arranged differently, its nucleus and the electron configuration is different, the wavelengths of light that can bounce those electrons around are going to be very specific depending on which element you're talking about. Every single oxygen atom is going to bounce electrons around differently than every single hydrogen atom. Every carbon atom is going to be different than every magnesium atom. And that's going to cause every element that exists in the universe to have its own fingerprint. Each one of these little lines that you're looking at, say each line for aluminum, would be an electron falling down from a higher energy level to a lower energy level. If we were to look at the absorption spectrum of aluminum, it would be the exact opposite of this. The photons that can bump the electrons to higher energy levels are going to be missing. All of these little lines, these are what are known as Fraunhofer lines. So if you see the word Fraunhofer line on a test, you know that it refers to these lines that are caused by electrons either absorbing or emitting photons. And when I say something is redshifted or blue shifted, I'm talking about Fraunhofer lines. I don't mean that the color of the object looks red to our eyes. I don't mean it looks blue to our eyes. I mean these Fraunhofer lines are shifted towards either the blue end of the spectrum or the red end of the spectrum. If we take a look at this particular element here, we can see that if it's just sitting still in front of us, this is where those Fraunhofer lines show up for this element. Now this element is in an object that's moving away from us. Each of these Fraunhofer lines are going to be shifted towards this red end of the spectrum by just a little bit. If that object is coming towards us, well, these Fraunhofer lines are going to be shifted towards the blue end of the spectrum. That's what red shift and blue shift means. It's these Fraunhofer lines that are shifted either towards the red or blue end of the spectrum. Depending on how much they're shifted, tells us how fast that object is either receding or approaching us. And now I want you guys to be an astronomer. I want you guys to take a look at this set of Fraunhofer lines that were observed from an element, and I want to see if you guys can identify that element. This one, we just have to make sure that all of these Fraunhofer lines are present, and it looks like the only element that has these lines exactly in the exact right places would be this element right here. So this is the Fraunhofer lines of helium. Try another one. Which element do you think this one is? Which element is missing these lines and these lines exactly? Well, let's find out. It's not continuous, not sodium, not mercury, and not lithium. It's none of them. It was a trick question. There are no elements, at least the ones that I've shown you, that have these exact lines missing. It has to match exactly. And if it doesn't match exactly, we know that it is not that element. A number of people wanted it to be lithium, but lithium should have a line right about here, and it doesn't. So we know that this is not lithium. So which element was that? Well, let's take a look. Which element has those? Which element has those lines missing and only those lines? Well, there's a red line and a green line and a blue line, and there is a line over here, you just can't see it. So that element is actually hydrogen. Sometimes you may see extra lines because there are more than one element in an object. In this case, of these four elements, which do we know exists in this star? Is it this one? Are we missing that line? No. Are we missing this line? Nope. Are we missing all of these? It looks like it. Are we missing this one? Yes. So we know that magnesium and iron are both present in this particular star. What about this one? Which elements are present there? Turns out that it is hydrogen and magnesium. This mystery star has which elements in it? It's got calcium and hydrogen. Hopefully you understand how to do this, because we're going to get to do this on a test. Try again. This one has calcium, iron, and magnesium. So it's got the Fraunhofer lines of 3 elements. It's missing hydrogen though. And because we know the exact wavelengths for every single element that exists, we can tell exactly which elements are in our sun's atmosphere, which I think is pretty cool. We don't have to go to the sun. We just look at the light, and we use spectrum analysis in order to figure out what the sun's made out of. If you could go back and answer the question that you wrote down at the beginning, I'd appreciate it.